In the last lesson, 6.1 polynomials, we classified monomials saying that they could only be the product of variables and numbers, and they couldn't have exponents different than those belonging to the set of whole numbers. And now we're going to talk about multiplying polynomials. This will require a lot of distribution. And we'll find later there's something called Pascal's triangle, which helps us to simplify binomial expansion, where we take a binomial base and instead of expanding it out a number of times equal to the exponent and then distributing ad nauseum, there are lots of shortcuts that help us figure out what the coefficient should be. That's where Pascal's triangle comes in. And there's always the same pattern involving the powers. So stay tuned for that. Right now I'm just going to work with the distributive property. And so I'll start you off, I'll pause the video, I'll finish it, and then unpause it, and the answer will appear right away. So if you need a little more help with these, then you could pause and work them out on your own. But if you feel confident in your distributive property and in multiplying monomials together, then you could just double check your answer real quickly as I go. So finding each product, I'm going to multiply this monomial to this binomial. So mono, bi, 1, 2, their product equals 2. I should get 2 terms after this. So I multiply coefficients together. 4 and 1 make 4. And then I multiply like bases, so then I add exponents. So y squared times y cubed is a total of 5 y's multiplied together. Repeated multiplication we summarize using an exponent of 5. And now I distribute that. 4y squared also to the 5, so 4 times 5 is 20. And the y squared doesn't have any other y's to multiply with, so it just stays y squared. And we don't factor, we are just multiplying polynomials together. So next we have a binomial times a trinomial, and so we are going to have 2 times 3 or 6 terms before we combine like terms. So I like to take the term with, the polynomial with fewer terms and distributing it across the other polynomial. So technically I should take a minus 3 and multiply it by 2 and then each of these terms separately. But to kind of skip a step, I will just take the a singularly and distribute it across to get the following. So check that out, noting that I already started to write it in standard form for polynomial, which means that the powers are in descending order. And now I will distribute the -3. Remember in higher mathematics, there really isn't subtraction, it's just addition of negatives. So I'm going to treat that -3 as such when I distribute. And I get that series of monomials. And now I'm going to combine like terms, so they have to have the same variables raised to the same exponents, and then you just operate on coefficients. So I noticed that I had an arithmetic mistake. That should have been a positive 2a when I multiplied a times 2. And with that fixed, I now have this cubic polynomial of 4 terms. So now I'm going to take a trinomial and multiply it by a trinomial, so I should get 9 terms out of that product. So technically you take this polynomial and you distribute it 3 times. But the shortcut of that is that I'm going to take this term and distribute it 3 times, and then I will take this term and distribute it 3 times, and then lastly I'll take this term and distribute it 3 times. You'll notice I used a trick. Since each of these polynomials were in standard form, and it also helped that no degree was missing, so I had the squared term, the quadratic term, the linear term, and the constant terms all present in both trinomials. when I distribute it, I started to line up the powers. So then it makes adding them together that much easier. We get the following answer. Now for the next problem, I'm going to pretend that I don't know how to use the patterns of Pascal's triangle and the patterns with the powers. And I'm going to expand here. Please resist the temptation to distribute an exponent. That thought should never cross your mind. There is no such property unless you're working with the power of product property. So if this was ab squared all raised to the third power, then we would be in business as we could write a cubed times b to the 6th. When you raise an exponent to an exponent, you multiply. Because we have addition in this binomial base, now we must use the definition of exponents to expand. An equal number of times equal to the exponent. And now you'll go through a pair of products at a time, simplifying them. That's the first product. And now I will take this binomial on the right and multiply it by the trinomial on the left, because then I can just load up one term, distribute it 3 times, and then load up a second term and distribute it 3 times, as opposed to loading up 3 separate terms, distributing them twice each. I think that requires more thinking and messing with your memory. So now I'll take this binomial and distribute it across the trinomial. After distributing and combining like terms, I arrive at that answer, a polynomial in standard form, so descending order. Please make sure that you alphabetize your variables in each of the products, so ab squared instead of 4b squared a. It helps to standardize like that, so it's increasing scannability, but also then when you have to combine like terms, everything's lined up for you. Same variables, same powers, operate on coefficients. Now, there is a shortcut, so instead of all of this work, and for then later if I had to, let's say, do x plus 7 all raised to the 4th power, I'll use what we're about to learn with Pascal's triangle to get that answer in 1 or 2 lines very quickly using patterns, rather than just algorithms that we just used to come up with the expansion of that binomial. So I'll get to the stuff that I have written down here in just a moment, but Pascal's triangle, it helps you to expand the powers of a binomial, such as what you see there. The coefficients of the terms form a pattern. It's often displayed in a triangular format. Note the following. Each coefficient is the sum of the 2 coefficients from the previous row. And then the exponents of the first term descend while those of the second ascend. I'll talk about that through an example. And if the second term of the binomial is negative, like let's say that was a negative, because of how powers work with negative bases, the signs of each term will alternate. So you'll pick up those shortcuts as we go. What I've done here in advance, written in red, is expanded out the hard way these binomials and then combine like terms. And notice I've included 1 coefficient where they occurred, because Pascal's triangle is concerned with all the coefficients, so we'll write them even if they are just 1. But I did not really write this in a triangular array, so it's going to be kind of hard to see the following patterns. I will rewrite all this using just a triangle of the coefficients. But notice we start at 1 because when you raise a binomial to 0 power, you just get 1. And then when you raise it to the 1st power, you just get it back. And I wrote in those coefficients of 1. Then when you square it, you get a 1 to start with, a 1 to end with. And then notice 1 plus 1 gives you 2 in the middle. And then again, you get 1 to start with, 1 to end with. So that will always be on the shelves or the slants of the triangle, so to speak. And then 1 plus 2 is 3. And 2 plus 1 is 3. And then you just have the 1 on the end. And then 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4. And again, on the ends, you have the 1s. Now, if I were the person coming up with this pattern, I would maybe just catch a glimpse that there is a relationship between the coefficients of the previous row. And then I would have to make sure to organize this a little bit better, which I will now do now, making Pascal's triangle. Here I have Pascal's triangle. So you start with degree of 0 like you saw before, x plus y raised to the 0 power. Now, you have to remember then that the first row deals with degree of 0, and then the 6th row deals with the degree of 5. So computer programmers won't really have issue with that because that's kind of how the index of an array starts. But for this, just remember when you're raising something to the 0 power, you start off with 1. So your row number is always 1 more than your degree number. So what kind of helps with that is, let's say you have a degree of 5, so that's like raising this binomial to the 5th power. Then what you're going to have is the first number in from either side will always equal, the coefficient anyway, will always equal the degree of the binomial. So the trick is look at the second number in from the right to figure out what the degree is of the polynomial. And so some people, when they make Pascal's triangle, for that reason, they kind of have zeros along the shelves. And so then if you look to the right of this, you get, well, a 0, so that's the degree of 0. You look to the right of that, that's a degree of 1. You look to the right of that. So the second one in is always telling you the degree. And then what's also useful about having the zeros along the shelves is that then you have the pattern a little more easily. So if you have here, that's where those zeros would actually go. 0 plus 1 is 1, 0 plus 1 is 1, but just know that it starts and ends with a 1 for each row, because now when you get to using this pattern, 1 plus 1 is 2, and then 1 plus 2 is 3, 2 plus 1 is 3, so that's how I'm creating all of those numbers. And that pattern continues on throughout this whole triangle. There's also a pattern. Now, again, Pascal's triangle deals with the coefficients. And then there is also a pattern with the powers. So I'm going to make the triangle again with subscripts of what the pattern is for those powers. This is what results. Notice that the powers of the first term descend while the powers of the second ascend. What do I mean? If you recall, when I expanded out x plus y, or I'll go through the first example here. So I have x plus y as a binomial to the 4th power. So the first thing I do is grab a coefficient from Pascal's triangle. I'll label those in blue. So the first thing to realize is because this is a degree of 4, I need to look at this row. Also, I will look at this row. They are the same, but the one on the right has the powers also listed. So the first thing that I do is grab a coefficient. All right, so I grab a coefficient of 1. And then I take the first term, I raise it to the 4th power, so there's the first term, raise that to the 4th power. And then I take the second term with its sign, and then I raise it to the 0 power. So let's see here, positive y raised to 0 power is just 1, so I'm not going to write it. Now, I go to the second term. That means I go back to Pascal's triangle because each of these terms consists of a coefficient and then a product of these two terms in the binomial with their respective powers. So I go back to Pascal's triangle, so I grab the next coefficient, which is a 4. That's positive. You need to add all these terms together. And then I go and I realize that I raise the first term, which is the x, to the third power. And then I raise the second term, which is positive y, to the first power. So just y. And I repeat this process for each number in that row of Pascal's triangle. So then I go back here, grab a 6 for the coefficient, and then I'm continuing to descend with the first term's power, and then ascend with the second term's power. Go back to Pascal's triangle, grab the coefficient, descend with the first term, ascend with the second, and grab the last coefficient from Pascal's triangle. Descend with the first term, so that knocks it down to 0, so I won't write x to the 0, that's just 1. And then I ascend with the second term in the binomial, so now that's y to the 4th power. And then you clean it up as needed. In this case, because the coefficients of the monomial terms in our binomial were each 1, we don't have anything to exponentiate and then multiply with the coefficient, so this suffices as a fully simplified answer. To review there, the numbers in blue were from Pascal's triangle, and then the exponents I could have written in green because they deal with the 4 and the 0, the 3 and the 1, the 2 and the 2, the 1 and the 3, and the 0 and the 4, noting that the first one, this term's power, descends. 4, 3, 2, 1, 0. And then the second term ascends. 0, 1, 2, 3, 4. And lastly, because they are seesawing past one another, they're inversely related, their sum must always equal the degree of 4. Looking at the next example, and the last one, I'm going to start putting in subtraction, and I'm going to put in coefficients so we can see what those are like, which will rely on our basics of the order of operations. So I need Pascal's triangle up to the 5th row. Once you practice with Pascal's triangle, you'll start to memorize rows, or at least remember enough of them that you could use symmetry because they're symmetric. So the blue will be coefficients, the green will be the powers, and then these are the bases. I'm going to expand this binomial using Pascal's triangle. So I take the first term, grab coefficient from Pascal's triangle, then I take just the t, and then I raise it to the 5th power. I take the negative s and raise it to the 0 power, and that's why I'm not going to write it, because that would just be multiplying 1t to the 5th by 1. So now I go to the next term. So I grab a 5 from Pascal's triangle, the 6th row of Pascal's triangle, because it's to a degree of 5. So I grab the coefficient, it's positive 5. And then I take the first term in the binomial base, which is t. I will raise it to the power of 4 because I need to start descending. And then I take the second term with its sign, that's a negative s. So I'm going to try to write that negative symbol a little higher so I don't accidentally make that a subtraction of t to the 4th minus s later. And then I raise that to the 1st power because its exponents are ascending, 0 and 1 now. Go back to Pascal's triangle, row 6, to get the 10 coefficient. I raise t to the fourth power, to the third power. And notice I'm not putting parentheses around its base just because it's a singular variable. And then the negative s, I do carefully want to put that in parentheses for this very moment because, boom, I'm raising it to an even power, so that's going to make its result positive. I continue this pattern grabbing from Pascal's coefficient triangle for the coefficient, and then descend, ascend, always splitting whatever the degree is, so that's 5, so 2 plus 3 is 5. Go back to Pascal's triangle, t to the first power, negative s to the fourth power, and then the last term, last coefficient, t is no longer there because it's to the 0 power, and then I'm going to take negative s and raise that to the power of 5. Alright, now I need to go through the order of operations, which, remember, we want to exponentiate before we multiply. So the first term is just going to be 2 to the 5th. Now the next term, I take negative 1s to the first power, and I get negative s, which I then multiply that by positive 5. So that gives me negative 5t to the fourth s. So that means I need to combine like terms. So that negative then multiplies by the 5 to create a negative 5. And then the next term, squaring the negative, will make that positive s times 10t cubed. So just no change there. But the next term sign will change because this is going to be a negative raised to an odd power. So that's going to be negative s cubed. Negative times the 10 will give us a negative 10t squared s cubed. The next one's positive because of the even power, so no sign change. And the last one's sign will change. And there's your fully simplified answer in 2 steps, thanks to Pascal's triangle and then the power descension ascension pattern. So notice, as I mentioned before, that every other sign will alternate when you have a subtraction in your binomial. And that's because the first term is to the 0 power, which is an even number. The second one is to an odd power, 1, then even, then odd, then even, then odd. So only the ones with odd coefficients will turn out to be negative, and so that's every other. So working through the next example, we not only have the negative here, so I'm going to use the shortcut for that, so every other term will be negative. And then I have to be very careful with my order of operations because I'll be raising 3 to different powers that I need to simplify before multiplying with the coefficient. So this is to the 4th power. And let's see, I start off with the coefficient of 1, so I won't write that anymore. I guess I will, just to make sure we're all on the same page. And I have 3x to the 4th power. And then negative y will be to the 0 power, so I'm not going to write that. Go back to Pascal's triangle. Now, it's a positive 4, but that's a negative. And so the pattern, as we see here, is that every other. So I'm just going to make that a negative 4. And then I'm not going to write that negative anymore. So I go ahead and descend with the 3x's power. And then I'm going to ascend with the y's power. Now, that should be a negative here and a positive here, but I'm just realizing a pattern and simplifying that ahead of time. If that doesn't work for you, then just write it out. It's not that big of a deal. And then next, I'm going to alternate the signs, so back to positive. Descend this power to a square. Ascend the y to a square. Now see, I know that's going to be positive because that would have been a negative squared, but I just resolved that ahead of time. Pascal's triangle for the coefficient. This is the other term, so I know it's going to be negative. And then I take 3x to the first power, and then I'm taking y cubed So technically I don't really need those parentheses. I'm just showing you that you take the whole base and you raise it to their exponents. And one more. So plus 1, 3, y to the 0 power, I won't write, and then just y to the 4th. So now I clean it up a little bit. Order of operations is very important here. I'm using the power product property, so that's going to be 3 to the 4th, x to the 4th. That's not distribution because there is no addition. And 3 to the 4th is 81, times 1 is just 81, x to the 4th. Now the next one, I'm going to go through this example very slowly. So I'm just going to write the negative 4, noting that I'm not multiplying it by that 3 because the 3 gets cubed, and so then that's going to be 27. And this is multiplication. This is a monomial, so everything is multiplied together. I should only have 1, 2, 3, 4, 5 terms in the end because that matches up with the number of terms in the row of Pascal's triangle. So then I have x cubed and then y, and then plus 6 and then 3 squared is 9, x squared, y squared, and then negative 4 times 3. I'll go ahead and I'll multiply that one together, so that'll be negative 12, xy cubed plus y to the 4th, and now simplify out those products. So 81 x to the 4th and negative 108 x cubed y plus 54 x squared y squared minus 12 xy cubed plus y to the 4th. So keep in mind that for the degree of 4, you need the 5th row of Pascal's triangle because the second number in is a 4. And in blue for Pascal's triangle, it just gives you the coefficients of each of the terms in your expansion. And then for the powers, they descend and then ascend. And the last thing is, for each of the monomials, please make sure that you follow the order of operations carefully. So exponentiate first, and then multiply with Pascal's coefficient. And then we saw that one pattern worked out here for us, that every other term sign will negate because the second term was negative here. But as you saw in the first example, you could opt not to do that just by carefully remembering that when you raise something to an even power, it goes positive, and when you raise something to the odd power, then it will be negative.